Thanks for tuning into this Revision Zone RAS video. In this video, we'll be going through some examples of differentiation and in particular, how to use some of the theory of differentiation that we saw in part 3 of this video series in actual questions. So let's jump straight into doing some examples. Obviously, the functions here are sort of standard polynomial functions. We're gonna differentiate them twice, no less. We've already seen how to differentiate these sort of functions. If you're not too sure, do just go back and look at sort of earlier videos in this series. I'll do this quite briefly. So of course we're going to be repeatedly using the formula. If I've got ax to the n, then when we differentiate it, we actually get the function a n x to the n minus 1, where a and n can actually be any real numbers. So perhaps I could write down here. So for a and n being any real numbers, we have the following formula. So we'll use that repeatedly, as I say. So the first derivative of this is just going to be 2x minus 5. I differentiate each term at a time. And then once I've got this function, the derivative, I can now differentiate this to be able to get the second derivative. So I would say the second derivative is actually going to be, we express it with 2 primes. If you remember, so I differentiate each term. The first term just gives me 2, the second term gives me 0, so the answer is just 2. So we've managed to differentiate our function twice. So that's the first derivative, and then that's the second derivative. Let's move on to part 2 of this example. Again, this is a very standard sort of function, so we do the same thing. We apply the idea in red, and we differentiate each term. So 4 times 3 is 12, so I get 12x squared. And then the power is 2, so I'm going to get 2x to the power 1, obviously, which I'm not going to write down 1 as something in itself explicitly. There's no need. And then 3x differentiates to give me 3, and the 19 would just differentiate to give me 0, so I need not write it down. So we've worked out the first derivative again. So since we have our first derivative in this case here, let me make it clear, and then we can differentiate the function in pink this time to get our second derivative. And of course, in Leibniz notation, we write down d2y dx squared. So the first term is going to be 12 times 2, which is going to be 24x. And then I'm going to have the 2x differentiates to just give me 2, and the 3 differentiates to give me 0. So that's the second derivative done. Let's move on to the third example. In this case, I'll try and do it to the sort of bottom of the screen here. So again, standard sort of function, because if I go back to my red statement, or the statement in red, a and n can be any real numbers. So indeed here, n happens to be minus 1 for x to the minus 1 term. So I differentiate to say h prime is going to be minus x to the minus 2 plus 4, right? And that's my first derivative, so let me just mark that in a different color perhaps. So that's my first derivative. I can now differentiate that in itself as a function to get my second derivative. So I'm going to get h double prime of x is actually going to be, so again looking at this first term here, it's going to be minus 1 times by minus 2 x to the power of minus 3, and then the 4 differentiates to give me 0, so I can just simplify this to say 2x to the minus 3. So with that, we've done the first example. Let's move on to the second example. So this next example asks us to work out the gradient to the red curve at the point 9, 12, and then we've got to use that to be able to calculate the equation of the tangent at the same point. So let's just have a go at this directly. So solution. So if the curve is y equals 4x to the half, and of course we work out the gradient by differentiating. So we just differentiate that directly, and we've already seen how to differentiate these things, so I'm just going to write the derivative down, which actually gives me 2x to the minus a half as the derivative. Now I want the gradient at the point 9, 12, which on the curve, if my eyesight is okay, it's going to be about there. It's going to be about there, right? 9, 12. So what I have to do is I have to evaluate my derivative at the point x equals 9. So I'm going to put that in. It's going to be 2 times 9 to the power of minus a half, and of course that's just 2 over the square root of 9, which is 2/3. So we've actually worked out what the gradient is going to be for that red curve at that green point. It's going to be 2/3. Now, we've got to work out the equation of the tangent line. So let's write that down. Equation of tangent. How we're going to work that out? Well, we know that every tangent to every straight line is going to have the form y equals mx plus c. So provided we have a gradient and we have a y-intercept, we know the line perfectly. So in this case, we know what the gradient is. We've already worked that out. That's 2/3. So we need to work out the y-intercept. So we're going to use the information that we know. We know that m equals 2/3, and we know that line satisfies point 912, i.e., I should say in brackets here, x equals 9 when y equals 12. So we sub all this in into our equation of a straight line. So I say my y is 12, my m is 2/3, and my x is 9, and then the plus c is there. And we simplify this, so we get 12 is equal to, let's just cancel these things here. So how many 3's go into 3? One number of 3's go into 9 is 3, and 2 times 3 is indeed 6. So I have 6 plus c, and that tells me c is actually 12 minus 6, which is 6. So now that I actually have a value for c, and we already had a value for m from earlier, I can actually say my equation can be written as y equals 2/3x plus 6. So we've managed to work out the equation of a tangent to our curve at the point 912. And just to do a light sketch here, so we've basically worked out the equation of that sort of tangent line, right? And that looks sensible. The line is going to pass around about 6, and you can see it's going to have a positive gradient. So moving on to example 3, we actually have the exact same curve and the exact same point, but now the question requires us to work out the equation of the normal and not quite the tangent. So before we actually jump into this in terms of doing the actual calculation, let's define what a normal is. So perhaps I just need to say that. So definition, normal, right? A normal, should write slightly better. A normal to a curve y equals f of x at a point AB, say, is a line which is perpendicular to the tangent to the curve y equals f of x at the point AB. At the point AB. So it's probably better to see this graphically. So if we come to our point which we'd marked earlier, let's mark that again. So I believe that point is going to be about here. So it's going to be 9, 9, 12. So let's look at a tangent to that curve. A tangent to that curve, as we established earlier, was going to look something like that, and it's going to pass through about 6, right? So what's a normal? Well, a normal is going to be a line going through the same point, but it's actually going to be perpendicular to the tangent. So it's going to be at 90 degrees to the tangent. So if I was to draw that, it's actually going to look something like this, and that angle there is going to be 90 degrees. So that's what a normal is. How do we go about calculating a normal? Well, there's a bit of theory in sort of in the theory of differentiation and so on and so forth, which tells us that so I should say fact, the gradient of tangent times by gradient of normal is actually equal to minus 1, right? This is commonly written in the form m1 times by m2 is equal to minus 1. Let me just put that in a pink box, right? Where m1 equals gradient of tangent and m2 is equal to gradient of normal. Let's have a quick think about why such a fact might actually be true. So it's not that hard to get one's head around. So let's draw an axis, let's say x and y, and we know gradients basically come out of triangles. So let's just consider an abstract triangle. So I've got something like this, say, right? So I've got A going across and B going up, and of course this triangle would actually define the gradient of this blue line, right? Or this triangle can be used to be able to work out the gradient of this blue line, right? So what is the gradient going to be in this case? Well, in this case, if I call this line L1, then M1 is going to be change in Y over change in X, obviously, which is going to be B over A, right? But now let's think about another line which is going to be at 90 degrees to that blue line. Well, we can get that by quite simply rotating our uh, red triangle 90 degrees anti-clockwise, say, right? So the A side would actually come on the vertical here, and the B side would actually go horizontal, and then that's going to be our hypotenuse, right? So because this side is A, this side is B, that's what I'm going to have. And of course, the important thing here is because we're actually moving, I should perhaps mention it in a different color, because in this case we're moving both to the right and up, both these are positive directions. But in the second case, we're moving to the left and up. So one of them is positive, but the other one is negative, right? So the gradient in that case will be negative, which is reassuring because the line is going to be pointing sort of downwards in that direction. So what do we have for line L2? For line L2, our gradient M2 is again going to be change in y over change in x, but our change in y is of course positive, that's just A, but our change in x is negative, which is minus B. So now we actually have a description, which I should mark here, for M1 and a description for M2. So let's work out what M1 times M2 is going to be. So M1 times M2 is going to be B over A times by A over minus B, right? But of course, this is just AB over minus AB, which is just minus 1. So this should convince you that actually uh, the fact that's mentioned earlier about behaviors of gradients of tangents and behaviors of gradients of normal is actually fairly sort of obvious. Now that we have the necessary background in terms of sort of the theoretical underpinnings, let's actually go on and answer that question. The equation is obviously y is 4x to the half, and the point is 9, 12, I believe. So since we have that, we can obviously differentiate it because we need the gradient of the tangent because we're going to be using m1 times m2 equals minus 1, where I'll just repeat it one more time. This is gradient of tangent, and this is gradient of normal, right? So what this formula would actually allow us to do is if we know the gradient of the tangent, we can go and work out the gradient of the normal, right? So going back to our derivative, so dy by dx is going to be 4 times a half x to the minus a half, which of course is 2x to the minus a half, which is 2 over root x. But obviously we want the gradient at the point x equals 9, which is 2 over root 9, which is 2/3. So this here is our gradient of tangent. So that tells us that m1 actually equals 2 over 3. Since m1 equals 2 over 3, we go to that formula and we say m2 actually equals minus 1 over m1, which is minus 1 over 2 over 3, which is minus 3 over 2. So we've actually managed to work out the gradient of normal. So gradient of normal at the point, and that's the important part, because if you change the point, you change what the gradient's going to be. So at the point 912 is actually has now been worked out. So since we know that, we go back to our standard equation. So equation of normal, because normal is a line, it's a straight line, it's going to be of the form y equals mx plus c. Well, in this case, what I mean by m is the gradient of the normal. So m actually happens to be m2, which is minus 3 over 2. And the point xy is obviously going to be, so x is going to be 9, like we saw in the last example, and y is going to be 12. So I'm going to sub all of that in into my equation here. So I'm going to get 12 is equal to minus 3 over 2 times by 9 plus c. So now we can start to tidy this up a little bit. So I can say multiply everything by 2. So I'm going to get 24 is equal to minus 3 times 9. Well, that's just minus 27 plus 2c. Well, that tells me what sort of this a description for c is. I can say 24 plus 27 is equal to 2c. Well, what's 24 plus 27? 27 plus 4 is 31, and then 31 plus 20 is 51. So c is actually 51 over 2, which tells me my equation of a normal is actually going to be y is equal to minus 3 over 2 x plus 51 over 2. And we've been able to work out the equation of our normal. So this is very reassuring. Moving on to the next example, we have to show that the function f of x equals x cubed is an increasing function. Well, let's get stuck in. Solution. Well, we know, so I'll say recall that a function g of x is increasing on the interval ab if g prime x is actually positive for all x being in that interval, right? So that's the condition for what it means for a function to be increasing. So we just apply that to our function f of x in this case, right? So we say f of x is of course x cubed. Then if we differentiate it, well, it's a standard derivative. It's actually going to give me 3x squared. Now we want to show it's increasing for all positive x, or non-zero positive x. Then we could say for x bigger than 0, we have x squared is bigger than 0. And obviously then if I triple everything, then that's still going to be bigger than 0, which is the same thing as saying f prime of x is actually bigger than 0. And therefore we can conclude thus f of x equals x cubed is increasing on 0 infinity, which obviously is the same as x being bigger than 0, right? And this can obviously be seen more sort of graphically. So if I draw the graph of x squared, which looks something like that, we can see xy, we can see that if I actually look at, say, tangents to the curve x cubed on the positive side, the tangents are all going to be pointing sort of uh, upwards in that sort of direction, which is precisely what it means for a function to be increasing, right? I should perhaps make a remark here. So remark is, of course, f of x is also increasing for all x actually less than 0, right? And that can be seen quite directly, which is if I take a tangent anywhere for x being negative in terms of the value of x, so x is less than 0 there, say, the tangent's all still going to be pointing upwards, which means the bottom part of the curve is also increasing and the top part of the curve is also increasing. So the only part that's actually neither increasing nor decreasing is actually the center here, because the gradient's going to be 0 there. Example 5 is slightly different in flavor to the last example, but it still goes back to ideas of sort of increasing and decreasing functions. So in this case, we're given a function f of x equals x squared minus 9x, and we're asked to find out where exactly that function is decreasing. So we've got to find out all the values of x for which that function is decreasing. So recall, actually, as we did in the last example, so f is decreasing when f prime x, should have said f of x, when f prime x is actually less than 0, right? So that's the condition we're going to apply on our function to be able to work out for what values of x the function is decreasing. So I differentiate f directly and I get 2x minus 9, which actually tells me, well, f is decreasing when 2x minus 9 is actually less than 0, and we can now solve this inequality fairly directly. So we add 9 to both sides, so I get 9 on the right-hand side, and then we just divide both sides by 2. So I just get x is less than 9 over 2. So we've actually worked out the interval. The interval is minus infinity to 9 over 2, right? So we say f of x is decreasing on the interval minus infinity to 9 over 2, and perhaps I can put that in a box so that's there as a standout sort of solution. Let's have a think about what's happening graphically. So if I was to actually just draw the graph of the function that we actually have, let's do it in red. So we know, let me factorize this function. So we know f of x is actually equal to x squared minus 9x, which can be factorized as x minus 9, which tells me that there's going to be two roots. There's going to be one here and there's going to be one at x equals 9. And of course, sort of because the first term of this there is actually positive, then we know it's going to be a happy-faced quadratic. So it's going to look something like that. It's going to pass through that, of course. So let me tidy that up a little bit, perhaps. Uh, okay, so this is looking slightly better. Good. So that's what the function's actually going to look like, right? That's what the function's going to look like. So from here, we shouldn't actually be surprised as to why we got the solution we got. So let's have a think. I should label my axes perhaps. So of course the vertex is going to be sort of halfway. It's going to be at this magical point in the middle, which is where there's perfect symmetry. But because that point is actually halfway, and this here is 0, and that point there is 9, then the point halfway actually has to have an x value of 4.5, right? So 4.5, I should write 9 over 2. Uh, so 9 over 2. And if we look to the left, and then if we consider gradients, say, on any part of the curve, say in that sort of region, right, we can see what's going to happen with the gradients. All of the gradients, right, are going to be pointing downwards. All the tangent lines at each one of these points is actually going to be pointing downwards. So indeed, this function is necessarily decreasing on the interval minus infinity 9 over 2. Moving on to the next example, we're given a cubic here and we have to find the value of x or values of x for which the second derivative of this cubic actually becomes 0. So we can directly actually solve this. So let's write down the cubic. Our cubic is 2x minus 3 cubed. So we're going to have to work out the second derivative, but we don't know how to differentiate functions which are in this sort of form, so we're going to have to expand this. So the expansion is going to look something like this. And of course, we could, for instance, just bracket two terms and then sort of expand the bracket using sort of normal techniques and then expand whatever we get from that with the thing on the right hand side on the outside. That's one way to go, but that's perhaps not the most efficient way. So what we could do is just use the binomial expansion. And the binomial expansion, if you've not seen before, then please do take a look at it. It's a fairly standard thing. It's on the A-level syllabus. So it's a cubic. So I'm going to have the main coefficients are going to be 1, 3, 3, and 1, and I'm going to have 2x everywhere, and I'm going to have minus 3 everywhere. So I'm going to have 2x everywhere and minus 3 everywhere, and again 2x everywhere and minus 3 everywhere, and 2x everywhere and minus 3 everywhere. But now here comes a slightly interesting part, which is the powers are going to be changing. So I'm going to start with a 3 and a 0, and then a 2 and a 1, and then a 1 and a 2, and then a 0 and a 3. So this is basically what we'll get once we've expanded three of our brackets. Let's try and simplify this. So 2 cubed is going to be 8, and then the x cubed is just going to give me x cubed, and then minus 3 to the power 0 is just 1, so we need not worry about it. Let's leave the 3 here for now. Actually, no, we can combine that 3 with the 3. So let me mark it. We can combine this 3 with this 3, and we can say we're going to get minus 9 times by 4x squared. And similarly, we come to the next term, and we can combine that 3 with these 3's in some sense, and we're going to get plus 2x times by 27. And lastly, the 2x to the power 0 is just going to give me 1, so minus 3 cubed is just going to give me minus 27. So I can write that down, minus 27, and now we're nearly done because we've actually got our cubic in the right sort of form. So 9 times 4 is 36, x squared, and 27 times 2 is of course 54. So that's our cubic, right? Now we differentiate it once, and that's the first derivative. 8 times 3 is 24, so I'm going to get 24x squared. 36 times 2 is 72, so I'm going to get 72x, and of course the 54x differentiates to give me just a 54, and the negative 27 differentiates to give me 0, so we will just leave that out. So once we've got this, we can differentiate it again term by term to get 2 times 24 is actually 48, and then the x is there, and minus 72x differentiated is just minus 72. And of course the 54, because it's a constant, you differentiate a constant, you always get 0, right? So once we've now got this, we can say we want our second derivative to equal 0. So what I'm actually going to do is I'm going to set this equal to 0, and I'm going to solve. So I'm going to say 48x is equal to 72, which tells me x is actually equal to 72 over 48. And we can simplify this to get the final answer of 3 over 2. So that's the x value for which the second derivative of our cubic actually gives us 0. Example 7 requires us to work out a value of p for a cubic, where we're told some information about the second derivative of that cubic at a particular point. Right? So let's have a look. So we're given a cubic, and we're told that at x equals minus 2, the second derivative is actually negative 1, and we have to find a value of p. So let's do just that. So let's write the cubic down. So f of x is actually equal to px cubed minus 3p x squared plus x squared minus 4, right? Where p is some number. So we're going to have to work out the second derivative. Before I just jump in and work out the second derivative, I think it's important to be able to collect the terms and express this in the right sort of way. So in particular, what I mean is we've got an x squared term there, and we've also got an x squared term there. So let's actually combine them. So when we combine them, I can factorize the x squared, of course, which is going to give me 1 minus 3p x squared minus 4. So now our cubic is in a sort of standard form. So let's now differentiate this. So the first derivative is going to give me 3p x squared plus the second term is going to give me 2 times by the coefficient, and then I reduce the power by 1, and of course the constant just differentiates to give me 0, so I just leave it at that. So that's the first derivative. The second derivative is I repeat the same process now, but to this function here. So 3p x squared, when I differentiate it, the coefficient remains, I multiply by 2, so I get 6p x. And then the term in the brackets is going to remain, obviously, and the x just differentiates to give me 1, so I've effectively got my second derivative. So now to use the condition that they've actually told us, I'm going to say f double prime at 2 is minus 1. Well, what is f double prime at 2? Well, our f double prime is actually here. So we're going to substitute 2 into that. So I'm going to replace x by 2. So I'm going to get 6p times by 2 plus, so 2, 1 minus 3p, close brackets, of course, right? And that's going to be equal to minus 1. So sorry, I should have written a minus 1 here. Minus 1. Good. So to simplify this now, I'm going to get 12p plus, and just to expand this sort of bracket, I'm going to get 2 minus 6p is equal to minus 1. But obviously 12p minus 6p is just 6p. So I'm going to get 6p plus 2 is equal to minus 1, which actually tells me 6p is equal to minus 3, which then tells me that p has to be minus 3 divided by 6, which of course is nothing other than minus a half. So we've been able to work out our value for p. In example 8, we're given a curve, and in this case we have to find all the stationary points and classify them as either being minimums, maximums, or points of inflection. So we jump in. So the first thing we want to actually do is, because we can't differentiate the curve the way it is, we want to rewrite it by expanding these sort of this bracket here, of course, right? So we're going to have x squared minus 4x minus 3, and we expand the brackets to get x cubed minus 4x squared, which is going to be from this term, and then finally we're going to get the minus 3x term. So we know that all stationary points satisfy dy by dx equals 0 as a condition, right? So we know that this is going to hold at all the stationary points, so we basically use this condition. We work out what dy by dx is in this case, the derivative, which is going to give me 3x squared, and then the minus 4x squared term is going to differentiate to give me minus 8x, and then the minus 3x term differentiates to give me minus 3, right? So we basically set our derivative to 0, and of course this is a quadratic, so we can solve this quadratic. So 3x squared minus 8x minus 3 equals 0. This can nicely be factorized in this case, so we need not turn to the formula. That's largely because 3 is prime. So I'm going to have minus 3 here and plus 1 here. So the solutions are x equals minus a third, or x equals 3. So we're going to have two stationary points, one at x equals minus a third and the other one at x equals 3. Let's work out the actual coordinate of the stationary point. So we're going to have to go back. We're going to have to go back to our equation of the curve and substitute in the x values to be able to get the y values, right? So when x equals minus a third, what's y? Y is equal to, let me go to this form of it because it's going to be easier to be able to work this out. It's going to be minus a third cubed minus 4 times by minus a third squared, and then minus 3 times by minus a third, right? Which of course is going to be minus 1 over 27, and then I'm going to get minus 4 over 9, and the last one's going to give me plus 1, right? So if I now simplify this a little bit, I'm going to get minus 1 over 27 minus, if I multiply top and bottom of 4/9 by 3, I'm going to get 12 over 27 plus 1, which gives me minus 13 over 27, which of course when I add 1 to it, I'm going to get 14 over 27. So we have a stationary point at minus a third and 14 over 27, right? So we can go and repeat this sort of thing for our second point, which is at x equals 3. Let me do it in a different color maybe. At x equals 3. So what are we going to get? So let's do this here. When x equals 3, y is equal to, again, going back to the expanded form of our cubic, it's going to be 3 cubed minus 4 times by 3 squared minus 3 times by 3, which is going to be 27 minus 4 times 9 minus 9, right? Which is going to be 27 minus 36 minus 9, which is 27 minus 45, which is actually minus 18. So our stationary point for the second one is actually at 3 and minus 18. So we've worked out two of our stationary points. Let's now determine their nature. We're going to use the second derivative test. We're going to use the second derivative test to determine their nature. Well, we know what the first derivative was. We just worked that out. The first derivative was 3x squared minus 8x minus 3, which then tells me actually the second derivative is going to be, because I just differentiate the first derivative, it's going to give me, 6x minus 8. And now we work out the second derivative at the two stationary points. So the second derivative at x equals minus a third is actually going to be 6 times by minus a third time take away 8 on the whole thing. So it's going to be minus 2 take away 8, which is minus 10, which is actually negative, which tells me that the stationary point at minus a third and 14 over 27, 1427, is actually a maximum. So let's repeat this with x equals 3. So I'm going to have the derivative is 6x minus 8. Obviously, this is the second derivative, I should have said. Right? So I'm going to get 6 times 3 minus 8, which is 18 minus 8, which is 10, which is positive, and that tells me that the stationary point at 3 minus 8, or minus 18 rather, is actually a minimum. Is a minimum. So we've managed to work out all the stationary points on our cubic, and we've also managed to work out what their nature is, to be able to classify them to say whether they're maximums or minimums. This one obviously has no point of inflection. It is worth just looking at the graph of the cubic just to see how these calculations translate to sort of a bit of geometry. So here we have a graph of our cubic, and indeed we can actually see that there are just two stationary points. Let me mark them in red actually. So there is one there, and then there's another one at the bottom here. And from the actual axes, we can see that the x value for one of the stationary points is 3, and for the other one, you see it's less than minus a half. So indeed, we calculated that to be minus a third, right? And the stationary point for the top one is actually minus a third, 14 over 27, and for the bottom stationary point, we've got 3 minus 18. And this is also consistent with what we said, which is the one at the top is actually a maximum, and this one here is actually a minimum, and there are no points of inflection, because obviously the cubic's going to behave, it's going to carry on going completely up and completely down, so there's going to be no other points which are going to be where the derivative is going to be 0. So I hope this helps you get a better understanding of exactly how to do these calculations of calculating stationary points and being able to determine their nature by using the second derivative test. The next example is quite different in flavor again to some of the examples we've seen so far. So in this case, we're told that we've got a general curve, and we're told that there are 2 points that are actually on the curve, and we're told the gradient at one of the points is 0, and we have to actually determine the exact equation of the curve. So what are we gonna do here? Let's think together. So we have to clearly use the information that we're actually given in the questions. We've got to use that, we've got to use that point, and we've got to use the fact that the gradient is actually zero, right? Uh, so let's try and put this to use. So the equation of our curve is of course ax squared plus bx plus c, and since we're told that since 1, 2 is on the curve, then we're going to have when y is going to be 2 when x is 1. So if I stick x equals 1 in that equation, I'm just going to get x squared as being just 1. So I'm going to get a, and then bx is just going to be b times 1. So I'm going to get b, and then the c is just going to be c. So I've actually got one, I've actually managed to get an equation from the fact that I know a point lies on the curve. The second thing I'm actually told is the gradient is 0, right? So I'll maybe highlight it again in a slightly different color, that the gradient is 0 at the point 2, 1. So I work out the gradient, so I differentiate my starred equation. When I differentiate that, the first term is going to give me 2ax, the second term is going to give me b, and the third term is of course going to be 0. So that's the general gradient that I've now worked out. I've got to set this equal to 0 at the point 2, 1. So x is going to be 2 at that point, right? So this basically tells me that 2a times by 2 plus b is actually going to be 0, which is of course the same thing as saying 4a. So let me say it here, 4a plus b is actually 0. So I've now got my second equation. So I'm going to need one more equation because I've got three unknowns, and then I'll be able to solve them simultaneously to work out the exact equation of our quadratic in this case. So how am I going to get my third bit of information? Well, since the point 2, 1 is where we worked out our gradient, because we know the gradient is 0 at that point, we also actually know that point must lie on the curve. So since 2, 1 lies on the curve, I can actually substitute the point into the star equation again. So y is 1 this time, and x is 2, so x squared is going to be 4, so I'm going to get 4a, plus bx is going to be 2b, and then the c is just going to be plus c, right? So this is my third equation. Now it's a matter of solving equations 1, 2, and 3 simultaneously. So we solve 1, 2, and 3 simultaneously, right? So let's have a think again. Let's write down. So if we actually look carefully, we see that parts of equation 2 are actually going to turn up in equation 1 in some sense, right? So let's try and substitute equation 2 into equation 3. Sorry, I called it equation 1 for some reason. So equation 3 can be rewritten as 1 is equal to 4a plus the 2b can be split up into b plus c. And now that part there is actually the same as what my equation 2 tells me, right? So I can substitute 2 into above. So when I substitute 2 into above, what do I get? I get 1 is equal to 0 plus b plus c, right? In other words, b plus c is 1. But I can now go to my equation 1, right? So I could say sub this into 1. So when I sub that into 1, I get 2 is equal to a plus b plus c is actually equal to, because I can put a bracket around here, is actually equal to a plus 1, which tells me a is nothing other than 1. But since I know what a is, then I can use equation 2 to be able to say what b is. B is going to be minus 4a, which is now going to be minus 4. So I've actually also worked out what b is. And perhaps there's enough space here for me to be able to scribble on the side. I can also write down c from this hashtag equation here, right? So I know c is going to be 1 minus b. So it's going to be 1 minus minus 4, which is actually going to be plus 5. So I've even managed to work out c. So we can now go back and write down what the equation must have been. It must have been y equals a is 1, so I just get x squared. B happens to be minus 4, so I get minus 4x, and C we've worked out to be plus 5, so we get plus 5. So we've actually been able to work out the equation of our curve. So let's take a look at the last example for this video. This example has been chosen deliberately because it sort of plays on our sort of usual thinking that we're always working with x. In this case, what we're actually going to be working with is actually p. So we're given a function, it's x squared plus px, and obviously the function is a quadratic, so it's not always going to be increasing or just decreasing. It's going to be sort of increasing for one part and decreasing for another. And we're told that for particular values of x, that the function is supposed to be increasing, and we have to find out what values of p the function must satisfy for it to actually be increasing on that interval. So what's the solution going to look like here? Well, we know that condition for a function to be increasing is actually f prime of x is actually bigger than 0, right? So in this case, since our f of x is x squared plus px, where p is some real number, then our f prime of x, this is very standard, I just differentiate it, I get 2x plus p. So I basically want on minus 1, 1, f of x is increasing, and so 2x plus p actually better be bigger than 0 on this x interval, right? On this x interval. So this is what I was saying. So here, our general instincts would be to solve this for x. But in this case, we're given something about x, we're told something about x, and we actually want to solve it for p, right? So I'm going to rearrange this to sort of say p has to be bigger than negative 2x. So now, from here, we should be able to deduce what the values of p must be, right? It's going to be a little bit awkward perhaps because one might not be used to thinking about these sort of things in this way, but let's try and think together. So the fact that x is an element of minus 1 to 1, that tells me that actually x is bigger than equal to minus 1 and it's less than equal to 1. But then if x is bigger than equal to minus 1 less than equal to 1, we need something about 2x because we have a 2x here. So I've got to go from x to 2x, so I multiply everything by 2. So I say 2x is bigger than equal to minus 2 and less than equal to 2. But of course, in fact, I didn't just need something about 2x, I needed something about minus 2x. So I multiply through by minus 1, and with inequalities that reverses the sign, right? So I actually get this. 2 is bigger than equal to minus 2, which is bigger than, sorry, 2 is bigger than equal to minus 2x, which is bigger than equals to minus 2. But of course, a perfectly normal way of writing that is actually like this. So we've now got a condition that minus 2x actually satisfies. And you see, so I want p to be bigger than negative 2x, right? Which is what we have here. Let me mark that in pink perhaps, right? So if I can only get the pink color, good. So we want p to be bigger than equal to minus 2x. Well, the biggest thing minus 2x can actually be is 2. So if we take p to be bigger than 2, then p bigger than minus 2x holds for x element of minus 1, 1. And so in this case, for our function f of x to be increasing on the interval minus 1, 1, our values of p must actually satisfy the fact that they must be bigger than 2 strictly. With that, I'd like to bring this video to an end. We hope you found this useful. If you did, then please hit the like and subscribe buttons. Do leave a comment in the comment section to let us know what you would like to see more videos on. Thank you for watching, and we will see you in the next video.